on this interval, with our random point, what if we were to make a bunch of other rectangles just like it, all different varying widths, with all random heights? So like that. And then like this, all based upon some random height in there. Okay, if we were to add these all up, we would also get some area under the curve. Do you guys agree? So the area of one of these rectangles would be f of c sub k times delta x sub k, and the sum of all such random rectangles would be the sum from k equals 1 to n of f of c sub k delta x sub k. This is what's called a Riemann sum. Notice the sigma notation denotes that it's a sum. Okay. Now, just like with the rectangular approximations that you guys did yesterday, the better approximation will come from having more what? Having more partitions, making the rectangles thinner and thinner and thinner, smaller and smaller and smaller, having more of them on your interval a to b. So what we're going to do here is we're going to use a limit. What if we say the limit as, and I think your book uses a simple p in here, p for partition. This is the limit as the norm of the partition approaches 0. I'll come back and explain this a little bit. Of the sum of k equals 1 to n of f of c sub k times delta x sub k, that's going to equal I on our closed interval a to b, where I is what we call the definite integral of f, which represents the area under the curve. Okay, this right here, the thing that I wrote down, is what is called the limit of a Riemann sum, because notice this part right here that I'm underlining is the Riemann sum. We throw a limit in front of it, we call it the limit of a Riemann sum. Now this part right here, let me get back to it. This is called the norm of the partition, and what this represents is the width of the largest subinterval on a to b. So let's just think about what this is saying. This is saying that we want the largest width that exists to approach 0. Norm of the partition approaches 0. So if we go back and look at our picture, it kind of looks like maybe this one right here is the widest one. Okay, so if I say that this particular rectangle that I'm highlighting now in pink, I want that width to approach 0. So it's going to get smaller and smaller and smaller. What do you think it's going to do to this next one over here, which is also quite wide? Well, once it hits that smaller one, it's going to force all of the smaller ones to be infinitely small as well. So if we say that the largest partition is going to get small, it's going to force all the smaller ones to get small as well, creating infinitely many little teeny tiny skinny rectangles, therefore equaling what we call the definite integral, which would be the exact area under the curve. Okay, if that sounds kind of weird, imagine just putting infinitely many, squeezing infinitely many rectangles into the space a to b. They would have to have a width getting really, really small, approaching 0. And that's what we're looking for right here. Now that limit of a Riemann sum is kind of long and kind of complicated to write out, so of course they came up with a much simpler little notation, and that's the definite integral, which looks like this. Okay, this part right here inside, in case you didn't know, is what we call the integrand, the dx. The x part refers to your variable of integration, and I know some of you guys will get really sloppy and will omit the dx or the dy or whichever variable we are using. You need to make sure you do write that, because later on it will matter if you have a dx in there or a dy. So let's just practice a little bit. Let's express the limit as a definite integral. So if I tell you we have the limit as the norm of the partition approaches 0 of the sum from k equals 1 to n of c sub k squared delta x sub k on 0 to 2. What is this equivalent in terms of an integral? So you look at 0 to 2. That's going to give you your lower limit and your upper limit. This right here is going to give you your function. So it's c sub k squared, so that means you have x squared, because c is some point representing x, and dx. It's as easy as that. Now, of course, I want you to be able to go backwards as well. So let's write this integral, x sine x dx, as the limit of a Riemann sum. Now, why is this important? You guys need to know where the integral comes from, and also I need you to be familiar with the term Riemann sum. There was an AP question a few years back where they mentioned writing something out as a limit of a Riemann sum, and many people did not know what it was, so I want to make sure you know. Alright, when you're writing this out as a limit of a Riemann sum, really it's not as hard as it looks, because a good chunk of it is always the same, no matter what. So this right here, limit as the norm of the partition approaches 0, sigma, so the sum from k equals 1 to n. This part right here is the only thing that changes. You will always have a delta x sub k on some interval. The only parts that you need to worry about that change are these two parts that I'm circling. Everything else, always the same, no matter what. So in this case, I'm going to put c sub k, sine of c sub k, on negative 1 to 2. Okay, let me write out a couple of definitions. So if y equals to f of x, and that function is non-negative, then we say that the area is equal to the integral from a to b of f of x dx. So basically area under the curve, but if we have some function and it is non-positive, what we're looking at is some function that exists underneath the x-axis, and we say that the area is equal to negative of the integral from a to b of f of x dx. And this brings us to our third one, which says that the integral from a to b of f of x dx is equal basically to the area above minus the area below. So if you have some curve like this from a to b that switches from being a positive function to a negative function, you want to subtract the region below because it's going to have a negative value. Let's go ahead and practice a few examples. And for now, we are going to be thinking of these integrals as areas. So if I have the integral from 1 to 2 of 5 dx, I can take out the constant 5, and so really all I'm looking at is a 1 dx, which is y equals to 1, a horizontal line, and we want to know what the area is between negative 2 and 1. So we can look at this in two different ways. You guys all should know how to integrate this right here. So we get an x from negative 2 to 1, which leaves us with 1 minus a negative 2, or 15. And you can also clearly see over here the area under the curve. That's a 3 by 1 rectangle, so that gives me the 3 inside and 5 times the constant on the outside. So the next one, I want us to use the graph of the integrand and their areas to evaluate. So what do we have if we have this x over 2 plus 3 as our function? So let's take a look. That has a slope of 1/2 and a y-intercept of 3. So we have a line with the slope of 2. If we have a line with a slope of 1/2, and we need to find the area of this trapezoid. So the area of the trapezoid is going to be 1/2 b1 plus b2 times h, which is 1/2 times 2. You need to find this height, and find this height, which happens to be 5, by plugging it in, times 6, which is the height across this way. So that gives us 21. Okay, one last one. Let's find the integral from a to b of 3t dt when a is between 0 and b. So you have some function, and it's y equals to 3t, and we're going to go from a to b. I don't know anything about it other than a is less than b. Notice we have a trapezoid, This right here is going to be the point A3A. This one's going to be B3B. So finding the area of that trapezoid is going to be 1/2 B1 plus B2 times the height, which works out kind of nicely, 3/2 times B² minus A² if you rewrite it.